So you've seen that marginal demand really tells me what do I have to do to the price, the y value, the value of my function, d of q. What do I have to do to price if I want to increase the quantity that I sell by just one more unit? If I just want to produce one more unit at a level of 800,000 units of production, then what's going to have to happen to the price? And one thing that you'll notice, we decided that in order to figure this out, what we should do is zoom way in on this point until we get something that looks an awful lot like a straight line, and then measure the slope of that straight line. And what you notice is that the slope of the straight line that we get is probably going to be different at different points on this graph. So for starters, if I sketch in a straight line that has that slope and which meets my graph at this point, q equals 800, then what I get is this line that I've sketched in here in purple. Just for the sake of vocabulary, we call this purple line a line that has the same slope as the graph does at this one point, and so it just barely kisses the graph at that one point and then moves on. We call this line a tangent line to the graph. Tangent line to the graph. Tangent meaning it just touches the graph at that single point, and then it moves on. And it has the same slope as the graph has at that single point. So we call it a tangent line. And the marginal demand, so based on what we talked about a few minutes ago, the marginal demand tells me the slope of that tangent line. So another way to think about what a marginal function tells us is a marginal function tells us the slope of a tangent line that we draw to the graph of that function. So if we think about what that actually is here, we did sort of a back of the envelope calculation to figure out that that slope was about negative 0.0005. If we bring that back into the units that are actually in my graph here. Here my units are in thousands and in dollars per unit. That slope actually, we move the decimal point twice and we actually get minus 0.5. So the slope of this purple line on the graph, if we bring it back to the units of the project, is this number, minus 0.586. So that's more accuracy than I was using in our calculation a minute ago. And because my Q is measured in thousands, what this is actually telling me is that it's the change in the unit price, not to sell one more unit, but actually to sell 1,000 more units. So the rate of change of my demand function is, I'm going to have to drop my price by 58 cents for every additional 1,000 units that I want to sell, starting from 800. So now you can see that if I just want to get this into a single unit basis, I would take and divide this by 1,000, which is where our 0.005 came from before. So the units in this demand function can interfere a little bit sometimes with the interpretation of it. So just be mindful of that when you are interpreting the values of these slopes in this part of the project. Okay. Now, a key observation that we can make is that the value, the slope of this tangent line, the marginal demand, is not going to be the same at every different place along this demand curve. If I'm producing 800 units and I increase my price by, I increase my quantity by a little bit, my price is going to fall by, half a cent, or actually, what was it? Not even half a cent. It's a 20th of a cent per unit. But that change, that slope, is different at different points on the graph. If I'm producing 400,000 units instead of 800,000 units, now my graph is slightly more shallow slope, right? That if I increase my quantity by a little bit, my price is going to fall, but it's not going to fall quite as quickly if I'm up at this level of production. Or even up here at this level of production, my slope is even more gradual. And so at different points along this graph, the slope is going to be different point to point. So one of our goals for the first half of today is to figure out how to quantify those differences. How do we come up with an equation, if we can, an equation that tells me the slope of this tangent line and how that slope varies from point to point? So that's where we ultimately need to get to. And that's where the new sort of calculus algebraic techniques are going to come in today. So let's see. So what's next? What I want to do is think about next how to come up with a formula that tells us the marginal demand at any given point. That's going to give us the new calculus strategy for today. So to do that, we want to, let me shrink my text here a little bit. We want to take this function, minus 0.00027 q squared minus 0.148728 q plus 558.223. We want to do something to that formula that can tell me the value of the marginal demand, not the demand, but the marginal demand at each of these different points. So how we're going to do that, I'm going to jump back to our live textbook here for a minute, is in the interest of time this semester, we're going to use the rules for what we call taking a derivative. We're going to use these rules off the shelf to look at how to come up with a formula for the derivative, the slope of a tangent line, the marginal value of a business function. We're going to use these rules to sort of black box our way into how to compute the formula for these derivatives. So what we'll do first is, let me actually go back to, where do I want to go here? Let's actually just create a new graph for a second. So let's just take a moment and think about the three various sort of parts that make up our quadratic function. Each of our quadratic functions is going to have a piece of the function which looks like an x squared, and whose graph is a parabola of some type. It's also going to have a piece which is just a multiple of x. If we just look at that piece, it's going to be a graph that has a straight line. And then there's a piece which is just going to be a constant, and a constant can be thought of as just a multiple of the number 1. And so the first thing that we need to know about how to compute a formula for a derivative is this linearity of derivatives formula, or theorem right here. What this theorem tells us is that if I'm adding together a bunch of functions or subtracting together a bunch of functions, or if I'm multiplying those functions by a constant, that I can compute the derivative of that combination by just doing each piece one at a time. So what that's telling me is that if I want to understand how to find a formula for the marginal demand, in other words, for the derivative of a function that has these three pieces added together, what I really need to know is how to take the derivative of the x squared piece, the x piece, and the constant piece. And I can take those derivatives piece by piece and then piece them back together. So that's what the linearity of the derivative actually does for us. So to get a feel for what this is going to look like, let's think first about let's think about the easiest piece first of all. So this is the piece which is just the constant function, y equals 1. If I wanted to know what the derivative for this function is, what I'm asking is, what is the slope of a tangent line to this function? Well, since this function is itself already a straight line, if I try to draw a tangent line to this graph, I'm just going to end up drawing the same line right on top of the graph itself. So then the question is, what would the slope of this line be? Well, since we're graphing a constant function, something we learn in pre-calculus is that anytime you graph a constant function, that graph is going to be a horizontal line. And the slope of a horizontal line, probably the most important slope in all of pre-calculus and calculus, is equal to 0. And the reason for that is that a horizontal line neither rises nor falls. And so the numerator, in the rise over run formulation of a slope, the numerator is always 0. So the slope of a horizontal line is equal to 0. So the first thing that we learn out of this, let me actually grab my notes here and bring them back into our screen. So here are some notes and takeaways for today. First is that a marginal function tells us how the function changes in response to increasing our quantity by just 1 unit. Put that in quotes. So we were thinking about marginal demand. It tells us how the price changes in response to increasing quantity by just 1 unit. Marginal revenue will tell us how revenue changes in response to increasing quantity by 1 unit, and so forth. And so now we're pushing forward into thinking about derivatives as an abstract concept in calculus. It tells us the slope of a tangent line to the graph of our function, y equals f of x. It tells us the rate of change of the dependent variable per unit change in the independent variable. That takes us back to this marginal idea. And it's going to tell me, as a result, it's going to tell me how the function increases or decreases at each of its points. So those are the things that the derivative of a function f of x is going to be able to tell us. And so if we think about the derivative of a constant function, what we decided was that because the derivative tells me the slope of the graph, for a constant function, that slope is always going to be equal to 0. As derivative 0. And so if my function is f of x equals 1, then the derivative, which we can denote by f prime of x, that derivative is just going to be equal to 0 for all values of x. So constant functions have a derivative equal to 0. All right, well, constant functions are something, but they're not a whole lot. We want to at least start to use some functions that model a change process in some way. So let's think about just the function y equals x. If I ask what is the slope of this function, or in other words, what is the slope of a tangent line to this function, because this function too is just a straight line by itself. If I draw a tangent line, I'm going to be drawing a line that's right on top of the graph itself. So the slope of a tangent line is the same thing again as the slope of the function, because this function is already a line. The slope of this function is the slope of the line y equals x and thinking of how y equals x matches the mx plus b template, well, b would be equal to 0 and m would be equal to 1. And so the slope of this is going to equal 1. And that's going to be true everywhere along the graph of this function. So if my function is f of x equals x, then its derivative is going to be equal to 1 everywhere for all values of x. So if f of x is equal to x, then the derivative, f prime of x, is going to be equal to 1 for all values of x. Again, we just get that from the geometric argument, right? We just say that the slope of a tangent line is the same thing as the slope of this graph, because the graph is already itself a line. So one thing we notice here is that even though our original function had an x in its formula, its derivative turns out not to have an x. Right? The x ends up going away. We're going to see in our next example why it is that that happens. It's an illustration of a larger phenomenon. So where things really get interesting is when we have a function whose graph is already not a straight line. So now when I have a function which is a curve, right? So it's not, the graph of the function itself is no longer a straight line. That means that if I choose a different place along my graph, I'm going to have a tangent line that has a different slope. So we need to figure out for those different slopes how to quantify them, how the value of the slope that we get relates to the value of x along this graph. So let's just start by asking, when x is equal to 0 on this graph of y equals x squared, what is the slope of the tangent line to that graph? I'm going to sort of keep track over here in a table. So when x is equal to 0, the slope of my tangent line, well, my tangent line appears to be horizontal here, so that slope is 0. Kind of keep track of my derivative. If I now increase x to be 1 instead of 0, now what's the slope of that line? Well, we can compute that slope just by eyeballing the graph. Let's label this point here. That would be the point 1, 1 on my graph. And then I'm going to pick another point on the graph of my tangent line. This would be the point 2, let's see, what is that? That's 2 comma 4. Actually, is it 2 comma 4? Or is that, no, sorry, it's 2 comma 3. I knew something didn't feel right there. There we go. So between those 2 points on my line, what I just need to do is compute the slope. And the slope is always a ratio of rise over run. The run here is +1. That's the difference in my x values, 2 minus 1. And the rise is the difference in my y values, 3 minus 2. Oh, sorry, 3 minus 1 is going to give me 2. And so the slope of this tangent line, and I'll write this out using the slope formula here, y2 minus y1 over x2 minus x1. That's +2 divided by +1. That slope is 2. So that means that my derivative, when x is equal to 1, that derivative is going to be equal to 2. And we can do that same process at a variety of different locations on this graph. For instance, if I slide this over to -1 instead, and I pick 2 points, -1, -1, and -2, or sorry, -1, 1, and -2, 3, and I compute the slope over there, I find that that slope is equal to -2. Then maybe if I slide my tangent line over here to x equals 2, and I pick 2 points, so that would be 2 comma 4, and then maybe I'll pick this point down here, just so it looks like the coordinates are nice, 0, -4, and 2, 4. If I compute the slope between those 2 points, y2 minus y1 is going to be 8, x2 minus x1 is going to be 2, 8 divided by 2 is going to give me 4. So at the point x equals 2, my slope is equal to 4. And what you find is that there's a pattern emerging in the various slopes that we're computing. All of the slopes themselves look like, if I plot them, they lie along a straight line. One last thing I'm going to do is just go back here to x equals -2 and find out if that pattern continues. Pick 2 points on my tangent line. y2 minus y1, 4 minus -4 is 8. x2 minus x1, -2 minus 0 is -2. So rise, 8 divided by run, -2, that's going to be -4. So when x is -2, the slope is -4. And the pattern that we see emerging over here is that it looks like, and the prediction that we'd make here, is that the slope of the graph y equals x squared is equal to, take a look at the pattern in this data. The slope that we're getting is just the value of x multiplied by 2. The slope is just double. When x is 0, the slope was 0. When x is 1, the slope was 2. When x is 2, the slope was 4. So the slope is, we predict, 2x. And it turns out that it is indeed true that at the level of formulas, if I take the derivative of the function y equals x squared, so if f of x is equal to x squared, then the derivative is f prime of x is equal to 2x. So if I want a formula for the derivative of f of x equals x squared, that formula is f prime of x equals 2x. And it turns out that we could continue this process of sort of experimenting, but mathematically, we can prove a theorem that tells us for any power of x how to compute its derivative. Notice what happened with x squared, that its derivative is still a function of x, which is still a power function, so it has an x in the base here, but the exponent on my x went from 2 in the original function down to 1 in the derivative. So that's the first thing that we notice about what happens with powers of x, is that they tend to go down when we take their derivative. The other thing that happened is that the multiple of my power started out as a 1 here, and then it turned out to be a 2 in my derivative. So it evidently, the derivative affects both the exponent of a power function and also the coefficient that's out in front of that power. And the general principle is what I've written down in our live textbook here as Theorem 321, the power rule for derivatives. So it tells me that for any power function, I can compute its derivative by a two-step process. The first step in that process is to multiply the expression by the exponent. So in the case of x squared, I multiplied that expression by 2. Multiplied by 2. And then the second thing I'll do is I'll decrease the exponent by 1. And so that's what this formula is telling us, that the derivative of the power function x to the n is n times x to the power n minus 1. Let's take a moment and jump into a web work problem to see how this works when the rubber meets the road recording. So there was a question, why do we bother with tangent lines at all if the equation for the power function itself is easy to use? And it's really more of a mathematical requirement because slope is really slope is a quantity that we can only really speak of as being a property of a line. Because we need, in order to define a slope, we need two different points in order to calculate a rise and a run. But when we think about derivatives, what we really want is to somehow measure the slope of a graph at a single point. But if I only look at a single point, I can't really compute a rise or a run. So it's kind of the derivative, or the marginal value of a function, tells me the slope of a tangent line. But what we end up doing when we put the context back into it is we kind of offhandedly say that it's the slope of the graph, and it tells me therefore, what is the response of that graph to a small change in the input quantity versus the output quantity. So let's next sort of talk about the mechanism for how do we actually compute a derivative function for a polynomial. In other words, a function which is built as a sum, difference, and scalar multiple of powers of x.